Okay, so today we're going to be looking at the experiment called rotational dynamics. In this experiment, we have a setup where we have this rotating platform. We have a string and some weight attached to it. I'll briefly show you the setup here. Okay, so here's our rotating platform. A pulley. We have some weight on this string here. We have this card so the motion detector can see it. Here's our motion detector. And we're going to be measuring the acceleration. So if we look up here, we can look at the different forces. We're going to call this rotating platter mass 1, and it has moment of inertia I. And we have two radiuses we're going to measure. The big R, the radius of the platter itself, and small r is the radius of the pulley where the string wraps around. So we can analyze the forces here. We have a tension of the string here, and we have a tension of the string here, and then we have the force of gravity pulling down on this weight, which is causing the acceleration. And that acceleration we want to both measure and predict, and we're going to compare our experimental data with the theoretical data. Okay, so a few concepts we have to look at is torque. So torque is the radius times the force. It's actually a vector cross product between the radius and the force, but we won't worry about that for this experiment. We have to look at the moment of inertia for a solid cylinder, where M1 is the mass of the platter, and big R is the radius of the platter. Okay. We also have Newton's second law, which we will use, and also Newton's second law for rotation, where torque acts like force, moment of inertia is analogous to mass, and alpha is angular acceleration, which is analogous to linear acceleration. So we're going to use both of these. We also want to look at the non-slipping conditions to relate linear acceleration and angular acceleration based on the radius. So alpha, angular acceleration in radians per second squared, times the radius, which in this case is the radius of the pulley that the string wraps around, in meters. So it gives us our linear acceleration in meters per second squared. Okay, so we're going to use Newton's second law to analyze this problem. So first we look at mass 2. So Newton's second law says the sum of the forces is equal to mass times acceleration. So we're going to take the direction of motion to be positive. So we have the force of gravity minus the tension equals mass times acceleration. And that's what we have written here. The force of gravity minus tension equals mass times acceleration. And note that this is mass 2. The mass hanging on the string, mass 2. Okay, so our goal is to solve for A, but we don't know what tension is yet. So we're going to use the definition of torque, which we looked at up here. The force here is going to be provided by the tension in the string. So we can rewrite that as torque equals the radius times the tension in the string. And now we can use Newton's second law for rotation to relate these two. Torque times I alpha. So we'll just equate it. So we have I alpha equals radius times tension. And we're going to solve that for tension. So tension equals I alpha over R. Now from this step in the lab, you're supposed to solve the next parts of the equation. So here's the hints I can give you. Alpha we can replace using this equation, right? Isn't alpha equal to A divided by R? So we can plug that in here. And I, we can plug in I, the moment of inertia of a solid cylinder. So we can plug both of these in for tension, and we'll have some relationship for tension. Now what do we do with that? We'll plug in what we have here after we plug the other values in. in for tension here. So we'll have some quantity here, and we're going to solve for acceleration. Now what you should find out when you do the algebra, you have acceleration here. You'll have a term of acceleration in here also. So you'll have an A here and an A here. So you're going to have to do some algebra to solve for that. So you'll have to move any quantity with A onto one side of the equal sign, factor out the A, and then divide what's left to solve for acceleration. And that'll give you a theoretical acceleration. And we're going to compare that to an experimental. So let's go ahead and look at the experimental portion of it. Okay, so as we saw our setup here, we're going to wind this up, and we can see the weight moving up here. Okay, so we'll wind it up to some point there. And I'm going to hold it. Before I release it, we're going to look at Logger Pro. And we're going to hit collect. And we'll see some data here showing up, okay? So I haven't released it yet. I just wanted to show you that. Now, looks like we need to extend our time of collection to maybe 15 seconds. All right, so let's do it again. Now I'm going to release this. So I'm releasing it, and we'll see the data on this one. Now that bump is when it hit the bottom and it bounced back up. As we can see, it's kind of going up and down right now. This thing's winding up, spinning around, and going back the other direction. So here, all we're really concerned about is this portion here. Again, our goal is to calculate acceleration. So how do we get acceleration? Well, we can use the slope of our velocity time graph. And let me auto scale that. So I'm just trying to make the graph bigger so we can observe the slope. There it goes. Okay, so we can see this portion of the data, so we can highlight that. Do a linear fit and our slope. Right here is our acceleration. Slope of velocity, that is our rate of change of velocity, is our acceleration. Our derivative of velocity is acceleration. Slope, all the same thing. 0.05948 meters per second squared. Okay, so that would be our first child for our experimental data. Now we're going to repeat this experiment. 3 trials for 4 different values of mass 2. And again, mass 2 is what's hanging on the string. Okay, so that is the basics of the rotational dynamics experiment. We're going to find an average value for each different mass, compare it to a theoretical value for each different mass that we calculate, and you'll show the calculations in your notebook. And we're going to compare it using both standard deviation of the mean and percent error. Okay, so other measured quantities, mass 1, the mass of the platter. So we'll have to take this off, measure the mass. Little r is the radius of the pulley that the string wrapped around, and that's where we use our vernier caliper to measure that. Big R is the radius of the platter. We can use a meter stick to measure that radius here. And I is calculated, but if that's in your equation, you can calculate that along with your theoretical calculation. So you can do it all at once. You don't necessarily have to do it at that step. You can, whatever's easier for you. Okay, and that, again, that's about the basics of this experiment, and I should have some data available for you to complete the calculations, and if you have any trouble with this deriving the theoretical equation, please contact me or your instructor, and we will help you out with those steps. Okay, thank you.